Okay, let's try to solve this example. This example is about finding electric field inside of a sphere with radius r and total charge q. Let me draw this sphere, something like that, with radius r and total charge q. And this q is distributed inside this sphere. All over the sphere, we have this total charge q. So in this consideration, we are going to find the electric field at this point. For example, at the point here, using Gauss law. Let me write Gauss law integral E dot ds is equal q in epsilon 0. And we want to find the electric field here at this point. And this electric field is exactly what mentioned here. For this case, I should consider a closed surface here. This is a closed surface S, and this is a closed surface. This is a closed surface. I call it a Gaussian surface. I will show it with S. This is exactly what I consider here. This is surface S, and this E is electric field on this surface. This is a spherical surface, so I can say that the electric field is in this direction. We are going to find this electric field, and this ds, let me zoom here to see it better. This is element of area. I will show it like this, and this is ds, vector of this area. This is perpendicular to the surface, and also here the electric field is perpendicular to the surface. I consider this area small, very small, to consider the electric field at all points here as constant vector. This is why we consider a small area here. At all points, electric field is constant. And you know that the angle here, the angle between ds and E is 0. So this angle is 0 here. Okay, let's come back to our equation here. So if I open this part, I will tell you later about this one, or we can talk about it now. What is this Q? This Q is all the Q inside this closed surface S. This is Q in, enclosed by this surface S. And you see that Q in is smaller than Q. It's part of it. So we will find it later. Okay, let's come back to our equation. I want to open this part. I can say integral and closed surface. This is closed surface. E dot ds. This is the dot product. So I can open it like this. E ds cosine. The angle between E and ds here, I will show you here. So I can write it 0 equal to Q in epsilon 0. Because electric field here just depends on distance. This is distance r, and the electric field just depends on this r. As I told you, the electric field is on the surface, and all points have the same distance. For all of them you have r. So I can say that the electric field on this surface is constant. At all points, the electric field is constant on the surface, so I can put it outside of this integral. And I can say that E integral ds is equal to q in epsilon 0. And you know the meaning of this. This means that we have to do summation, this summation here. I will show you. You should do summation a small area because you divided this area into small pieces. And you should do summation here for all pieces. And the summation is all the surface area, the entire area of the surface S. This is the meaning of this part. The meaning of this part. So I can say that this is 4 pi R2. And overall I can say that 4 pi R2 is equal to Q in epsilon 0. Okay, let's find this Q in. For finding Q in, you can use this equation. Q in is equal to rho, that is the density of charge multiplied by V. I will show it with S because this is the volume of this closed surface. This is the volume here, and rho is the density. So let's find this. This is equal to rho, and Vs is 4 over 3 pi R3. And rho is the charge density. Rho is equal to Q over V. This V here, V is the volume where this charge Q is distributed. So V is the volume of the bigger sphere, and Q is exactly the charge distributed over this volume. So I can say that rho is equal to Q 4 over 3 pi R3. Okay, let's call this equation as equation 1, this as equation 2, and this as equation 3. So from these equations, 1, 2, and 3, I can finally say that by just combine them together, and you can finally find something like this. E 1 over 4 p epsilon 0 R2Q R3 divided by R3. If I simplify it, I can say that this is 4 pi epsilon 0 Q R3 multiplied by R. This part is constant, this part is constant, and you see that E is just a function of R. It changes linearly. If, for example, we found E in the center, R is equal to 0, I can say E0 is equal to 0. As on the surface of this area, where R is equal to R, you see that electric field is equal to 1 over pi epsilon 0 Q divided by R2. This is what we expected. Okay, that's what I wanted to say about this example. And this way you can solve this kind of examples very easily.